In our previous research, in 2010, Leiva introduced an algorithm that solves the express service design problem over a corridor, but there are some limitations. First, we need to work with an a priori set of candidate services, meaning that we are going to feed some options to the model, and the model is just going to focus on defining the frequencies for these services. We are not, oh, we are allowing passengers to transfer in this model. We are assuming passenger assigning to be deterministic, and this is the key of this presentation. This is what we're going to try to improve, or what we have improved and what we're going to show you now. And that bus capacity is taken into account via a greedy heuristic. It's not easy to design the services while at the same time considering passenger assignment and bus capacity. Because if you limit bus capacity, then some people are going to be the first ones there to use this capacity. So in a first approach, what we do is that we neglect capacity. We forget about capacity. We assume that everyone is going to be able to do whatever they want to, and then we're going to fix the frequencies of the system so we can meet this demand. Then Larraín et al., that means me and Juan Carlos and some other people, extended this work, and we generated services to fit to Leiva's model, heuristically, and we also proposed an algorithm to work with networks, amongst many other smaller improvements in coding and algorithms. So the problem framework, the way we tackle this problem is by dividing it in smaller components. So we have the general limited stop design problem as the main objective of our work. And first, to deal with it, we separate the problem between service generation module, where we generate the services to fit to the problem, and then we solve the problem here. And then to solve that problem with capacity, we will solve the problem without capacity, like I explained before. So we can iteratively fix the frequencies till we meet capacity constraints. So the problem at the core of the LSDP is this problem here we call the FOAP, which is the frequency optimization and assignment problem, where we have to define or set the frequencies of the services while at the same time trying to model passenger behavior correctly. So we have to deal with two things at the same time. The frequency optimization and assignment problem looks like this. We have a set of a priori services like this. We are depicting 5 here. And we have to decide the frequencies of these services. And how do we do it? We minimize the social costs, which are comprised of operator costs, waiting time for the users, the travel time of the users, and finally the transfers that users will make. And this is subject to, of course, non-negativity of the frequencies, although some of them might take value 0. Some of these services might not be useful for the scenario that we are modeling. We have to model flow conservation because we're dealing with transfers, bus conservation, of course, because we might work with some services that are short-turning or whatever, so we have to deal with frequencies as well. And also we add some frequency bounds for algorithmic reasons that I'm going to explain later. So the limitations of the current approach are the following, and these are the limitations that we're going to face in the rest of this presentation. First, we have that the associated mixed integer nonlinear problem can only be solved reasonably for instances of limited size. Second, we have that deterministic behavior leads to this all or nothing assignment, which can be really very unrealistic. When you have this deterministic assignment, you have these situations where a tiny increase in frequencies for a particular service might change the way everybody behaves. And that's really, really annoying where you're dealing with iterative models where capacities are adjusted iteration by iteration. If you make a small change and everybody change the routes, then you're going to have some problem adjusting the capacities or the frequencies. And third, We have that passenger assignment comes from minimizing social cost. So we can just let everybody do whatever they want to without taking into account directly the bus capacity, and then we're going to fix capacity by using frequency bounds in the model, and we're going to deal with this iteratively. But the way we do it now, since we have to solve the FOAP many times, we were doing it in a greedy way, and now we're going to extend it to a grasp algorithm. Since we're improving the solution of the FOAP, now we can solve it many more times, so we're going to test another approach, more ambitious approach for that. So these are the three main problems. Now we're going to talk about these new ideas for the LSDP. In particular, we're going to make some suggestions to tackle each one of these problems. Regarding the first one, the difficult model that we had to solve, our approach is to implement a bi-level solution for this problem. Instead of solving the frequency and assignment problem all at once, we're going to separate it in two stages that we're going to solve iteratively. Second, since deterministic behavior can be troublesome, we're going to try to model assignment as a stochastic process. And third, as I mentioned before, we're going to try to improve the capacity algorithm, extending the gridded formulation to a grasp formulation. So let's talk about the bi-level solution of the problem. We have this frequency optimization and passenger assignment problem that we were solving simultaneously with as one optimization problem. Now we're going to separate it naturally between frequency optimization and passenger assignment. And we're going to iterate until we find convergence. The frequency optimization problem takes as input the services that are being used, the passenger assignment, and then optimizes the frequencies for the services. And the passenger assignment problem will take a given set of frequencies and is going to predict the way passengers behave. So in the context, in the framework we proposed before, this problem, the FOAP, is going to now be subdivided into the FOAP and the POP, which are the frequency optimization problem and the passenger assignment problem. And this separation not only is going to give us better solution times, also this separates the passenger assignment is not necessarily going to be in the form of an optimization problem. So now we can model assignment the way we want to do it. And that opens the door for a stochastic passenger assignment, which is what we're going to discuss now. So first of all, let's speak about deterministic assignment, because stochastic assignment starts from this. So let's put ourselves in this scenario. Let's say that you are at a stop A here, waiting for a bus to go to stop B. And you have two options. You can take the regular service, which takes an hour to get there, and with a frequency of 10 vehicles per hour. And then you have this express service that saves you 10 minutes, but it's a little less frequent than the other one. So the question here, first of all, we have to observe that even if this service, if its frequency was really low, if you're waiting at stop A and this service shows up, you don't care about its frequency. You consider yourself lucky, you take it, you get to your destination faster. So the real decision here is, what about, it's written over there. What if the regular service shows up? Should you take it, or should you wait for the express service? So if you take it, you have no waiting time, and you have a travel time of 60 minutes, 1 hour. And if you leave the regular service, you don't take it, then you will have to wait for 5 minutes, should be 3 minutes. Assuming that the buses arrive uniformly to the station, then the expected value of your waiting time should be 3 minutes, not 5, and your travel time would be 50 minutes. So this option has a cost of 60 minutes, this option has a cost of 53 minutes. In this scenario, you would let the regular service go, and you would wait for the express service. So every time we are dealing with an isolated OD pair, you can perform this kind of analysis, and this will yield a set of attractive services, the services that you will be willing to take in order to minimize your expected travel time. So the assignment process, when done deterministically, consists of three main steps. First, we're going to find the attractive services and the expected travel time for every OD pair, like in our previous example. Then, on the resulting network, we're going to assign trips to the shortest paths to find where people do transfers. And in the end, we're going to load the assigned flows to the original services. This will look kind of like this. So we can take a network like this one, where different colors represent different services, and we're going to assume that the flow is always going in this direction from A to E. So the first step is to solve the attractive line problem for each OD pair. So it would look something like this. We're isolating now pair AE, but we can work with any pair. We have to work with all OD pairs. And if we isolate A to E, we can see that we can go from A to E using the red line directly here, the light blue line also here, or the green line which goes through D. So these are the three options, and from these three options we solve this problem. We compute the expected travel times, and we choose the smaller one. So that way we transform this system of lines in just one single arc, representing going from A to E. If I go from A to E, I should use this set of attractive services, and this is the expected travel time that I will get. So we simplify the problem from this to this. And then, of course, we're going to do the same thing with every other OD pair. Then, on top of this network, we solve the second stage, which is finding the shortest paths for every OD pair. Looking at station A, stop A, it would look something like this, right? For instance, here we can see that we're saying that if you go from A to E, you're willing to transfer in at B, here. It could be some other way, but this is just for this example. And then we have to compute the ridership for each service from this information. So if, for instance, we have 100 passengers traveling from A to C using this arc, and let's say that arc was using both services, we might have that those 100 passengers are divided like that. And then we take another trip from A to B. Let's say that we have 80 passengers traveling from A to B, and then we're going to say that those passengers are going to use those three lines, and you can split them among the three options like that. And then you have to do that with every OD pair, but this is the way deterministic assignment works. All right? So now let's talk about stochastic assignment. How are we going to adapt this procedure to consider some source of randomness? So there are many ways that we can do this, but the way we implemented it was to add a component of randomness first in how people choose their attractive lines. So far, what we did was to compare the possible set of attractive lines and finding the cheapest one. Now we're going to say that there's a probability of choosing a particular set. And then for route choice, we were assigning passengers to the shortest path. Now we're going to assign them stochastically between a set of attractive or fast routes. So for the stochastic, for the attractive service part, we're going to take the same isolated OB pair that we took before, but now instead of just finding one combination of services that minimizes our expected travel times, we're going to compute the travel times, the expected travel times for different combinations of services, and then we're going to assign a probability to each one of them, which is going to be somehow proportional to how fast that option is. And then we're going to, like in the previous case, reduce this to a single arc with an expected maximum utility in this case, but with a value of traveling from here to here. With this, that gives us an expected travel time, just like before, but now considering that people might split between more options than just one attractive set of lines. The way we do it is using the very well-known logic formula for this, and the expected maximum utility is computed using the log sum expression, like that. And then, for route choice, we're going to use, or we use Dial's algorithm, which is a way of assigning trips to a network in a way that the result, that the utilization of each route corresponds to what a logic model would yield if we fed it the list of routes and we use the logic model to predict the flows. So we might get that some people use this road, some people use that combination, and some people will use that combination, and so on and so forth. So the total demand, the step 3, I'm not going to illustrate it because it doesn't really change, but can be obtained like before, but taking into account that now we have probabilities, so it's a little bit more sophisticated, but it's not that hard to do, so it's pretty straightforward. And the third improvement is that we're going to, we use the grasp capacity algorithm instead of a greedy one. The greedy heuristic for the FOAP worked like this. We would solve this, we would solve the frequency optimization and assignment problem, and we would obtain a set of frequencies. And then we would look for a line L that shows capacity deficit. We would look for a particular line that it's overcrowded. And then we will select the line with the greatest overcrowding, with the greatest deficit of capacity. And then we would set a lower bound for this frequency. We would estimate the frequency that we need. So to eliminate this problem, we would, at this lower bound, we would resolve the FOAP, update the solution, and then iterate until we find a solution where no lines are overcrowded. But this is a greedy algorithm because we're always selecting the line with the greater capacity deficit. If we want to extend it to a grasp algorithm, we just need to change one line of code, basically. We take the greedy heuristic, and then instead of selecting this particular line, we select it randomly from the list of lines in deficit. And usually you would use probability distribution, which is more likely to choose the lines with a bigger deficit anyway. But that's just implementation issues that I'm not going to explain now. Of course, this procedure just gives you one solution. If you run this one just one time, it's going to give you one solution. But if you run it many times, you're going to get several different solutions. So the idea behind this is that we can now do this many times. We wish, or we hoped, that the FOAP was going to work faster, so we would be able to do this many times and obtain different solutions and compare them and take the best one we would find. So how did this all work out? We worked on three corridors with real world data obtained for corridors in Pajaritos and Grecia, the yellow and the red line, which are corridors here in Santiago, and also the black line, which represents the Caracas corridor in Transmilenio, is the main corridor in Transmilenio. And for each of these three corridors, we created instances with with 20, with 40, and with 80 stops per direction. No, in total, 80, 20, 40, and 80, and we adapted the demand matrix to fit the number of stops we wanted to work. So this way we created 9 scenarios to start. And then we performed this experiment where each of these 9 scenarios was solved using different variations of our algorithms. So the algorithms were, first of all, we worked with the deterministic problem with no transfers, and we used greedy and grasp. Then we worked with the deterministic model with transfer, with greedy and grasp, and then we did the stochastic assignment, of course with greedy and grasp, and also with transfers. Each one for the 9 scenarios. And we took as benchmark the algorithm A0, which optimized the FOAP simultaneously instead of doing it with this bi-level approach we described. So these are the results. We have the 9 scenarios, Pajaritos, Grecia, and Caracas, with 20, 40, and 80 stops. And these are the different algorithms. We use also as benchmark the solution you get when you use no express services at all. So then we compare and we report the savings instead of big numbers. So the bigger this number, the better the results. So the first thing that we observe is that if we look here, no, there should be a, yeah. No, it should be this column and this. No, it's all right. This column, I'm sorry. First of all, we wanted to make sure that when we solved the problem using the bi-level approach, we would expect it to converge faster, but it might converge to a local minimum solution. And in that sense, the simultaneous approach had a little advantage because it was being solved by using a commercial solver, and it might be better at finding global optima. But the case we're showing here is that there's little variation in the results. And sometimes we even improve it drastically, like here. So we're not losing the quality of our solution by simplifying the solution algorithm, by applying this bi-level approach. Second, we could observe that transfers seem to have a bigger impact as demand grows. And we can observe that comparing this column and this column. This is no transfers, this is transfers. And the bigger instances in terms of demand are the ones here in Caracas. So you can see that savings go up here, and go up here, and the difference is bigger than the other cases where demand is lower. So as demand increases, transfers have a bigger impact when designing express services. The third thing we could observe is that greedy algorithms weren't really worth the effort, because we would take a lot of time optimizing instead of running just one time the algorithm. And really, we have to run it many times. And if we compare the results, we can see here, we can compare greedy and grasp. We can see that the results are basically the same, but we have this one here, which confirms at least that the greedy algorithm might lead you to suboptimal solutions, might lead you to local optima, as we know. But it's interesting to see that in only one of the instances, the grasp algorithm was able to improve what we were already getting by the greedy approach. So the greedy approach, bottom line, is not that bad. And finally, in this experiment at least, we couldn't find any observable trends when working with stochastic assignment. probably because this problem was way harder to solve, and we're still working on a specific solution algorithm for this one. Maybe the solution algorithm that we're using now lead you to savings. I mean, these are positive numbers, so we're achieving savings when compared to working without express services. But we can do better. We know we can do better. But for now we can instead of looking at these numbers, we're going to look at the solution and try to take a closer look at the way the services behave when optimizing, when dealing with stochastic assignment instead of deterministic. We're going to take a look at that later on. Also, we wanted to take a closer look at the effect of transfers in a problem. So we defined 4 scenarios of 4 different types of algorithm. The first one is first we work with no transfers, and then we try these 4 variations which are allowing transfers the same way this result was reported in the last table. But now we also try this thing we called the bidirectional transfer. And the difference here is that since you have a bidirectional corridor, sometimes people are going to ride against the direction of the trip. In this kind of transfer, we weren't allowing that, and then we decided to give it some additional flexibility to allow people to ride against their direction to be able to catch the express service. Sometimes you might want to go back 1 station, so you can save a lot of time using the express service. So that's a bidirectional transfer. And then, as a way to find a bound on the potential savings that we can achieve using express services, we said, what if transfers are free? And by free, we mean that you're not going to pay for it, of course, but also that you're not going to have to walk or suffer any kind of annoyance because of changing, switching, or making this transfer. But we still have to wait for the new service to come. We're not assuming perfect synchronization here. We're just assuming that you're not going to have to walk a lot or pay for an additional fee. And we can confirm that the effect of express services is much greater when transfer costs are reduced. So this trend that we observed before is confirmed, and we can see that if we make transfers smoother, then we can design better express services. When we take a look at solution times, we can see that first of all, the bi-level approach saves a lot of time compared to the simultaneous approach. And keep in mind that we were getting basically the same results. So we're saving a lot of time here. Then when working with greedy algorithms, with grasp algorithms, of course the solution times will increase. This is the number of iterations we're performing. And even we found this weird thing at first, that if you take the solution time here and you divide it by the number of iterations, you get a higher number than here. And that's because the greedy way to solve the problem gets to a faster solution. You get less iterations of frequency bounds adjustments. If you're adjusting the lines that are not overcrowded, then you're going to take more steps to find a feasible solution. So it takes longer on each iteration as well. And as I said earlier, even though in theory we would expect grasp to behave quite better than greedy, we only could find 1 instance where this actually happened. So it's a matter of taste, or how much time you have available to invest in the solution. And the solution of the stochastic problem takes a lot of time. Takes a lot of time, because solving the stochastic route choice problem takes quite longer than Dijkstra's algorithm to find the shortest paths. So the bi-level approach finds good solutions in just a fraction of the time. This is the main takeaway of this table here. And finally, we performed an experiment to look at the shapes of the load profiles on the solutions. How is stochastic assignment different from deterministic? And I think these graphs speak for themselves. We have at the left side the results using deterministic assignment, and at the right side the stochastic assignment. And this is not only an assignment, this is optimizing the frequencies and designing the services, taking different assignments into account. And you can see here that you're designing a line for a load profile that is very spiky and very, I wouldn't say that this solution is pretty robust. This is very, very unlikely to be what you will see on the street. And then you have the stochastic assignment that gives you these smooth curves, much more realistic. Then on this left-hand side, you have a higher number of services. Here in these graphs, I'm making visible the all-stop service, but you can see the shadow of many, many, many other services on the corridor. So we have a really, really huge, a really big number of services here, and many of those services are designed to work at capacity on a long, long part of their route. And then you have the stochastic case where you use not as many services as here. The load is spread among the services. You can see here that you have some services that are working on capacity and some services are down here. Then you have this, that all the services have a similar curve here, and also that you have a peak of capacity which defines the frequency, but you don't have a service that shows this sort of plateau here, where you have a long part of the route that works on capacity. This is much more realistic. So stochastic assignment gives more robust solutions, spreading demand among services instead of saturating a few of them, which is, I insist, more realistic and way safer if you're looking at it from the design point of view. One interesting thing we wanted to find out, given that we have these two kinds of assignments, is what if? What if we design for deterministic passenger assignment, but in reality, passengers were behaving the other way? All right, so we're going to take this solution, the set of services behind this chart here, and we're going to assign passengers stochastically to those services. Of course, without imposing a capacity constraint. We're trying to show what is the desire of the passengers here, and we obtain this thing. The red line here is bus capacity. So the thing we're observing here is that deterministic passenger assignment tends to underestimate the utilization or the potential demand of the all-stop services or the all-stop-like services. So, and that's pretty reasonable, because when you have deterministic assignment, you reach a point where people are going to say, I'm going to take the express, I'm going to ignore the regular service. And that moment it's all or nothing, you know? So if you consider stochasticity, then you know that this is a smooth process, and that even when deterministic assignment predicts that no one is going to use the slower services, in reality, many people might be still willing to take it. And this is what we're seeing here. So when we work with deterministic assignment, we are being a little bit naive and maybe over-optimistic. We are maybe overestimating the ridership of the express services, and this would be a safer approach, even though we still have a lot of challenges to face regarding the correct way of solving this design problem in this case. So, in conclusion, we have introduced formally the LSDP and in particular the FOAP, which are two problems that we deem necessary to be able to tackle the design problem for express services. Second, we have improved solution times for the FOAP and consequently for the regional problem using this bi-level approach. Third, we have shown that stochastic assignment leads to more realistic and robust solutions, even though we still have to find a better way to solve it. Allowing for transfers during service design can lead to better solutions. We have seen that reducing the nuisance associated with transfers can improve the performance of limited stop services. And for future research, we want to tackle the issue of capacity at the bus stop level, which is a constraint that is active in practice in systems such as Transmilenio, where you can see that not only the buses are overcrowded, but also the stations, and the bottleneck of the system might be shifting to this part of the problem that we haven't taken into account so far, but we are already working on that with a student, and we expect to be able to show results pretty soon. And another future avenue of research consists in expanding the problem of the network design problem, designing express services for a network of corridors. As I mentioned before in a previous research, I proposed an algorithm, but now we have to test it and implement it on big instances. We're working with data from Transmilenio, and we also expect to be able to show results for that in the following years. So that's all I had prepared, and now I will take some of your questions if you have any. Thank you. Daniel. Yeah, that's the greedy approach. Yeah. 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 Yeah, there's a difference because when you, sorry. Yeah, yeah. So Daniel's question has to do with the greedy and grasp algorithms. He's asking, what difference does it make to use the greedy approach since you're going to have to fix all the capacity problems anyway, right? So the difference is that when you solve the problem, the overcrowding problem from one bus, people reassign. And then the problem might move to a different place of the corridor. The system is very volatile, so it changes a lot when you change one frequency. So but that might explain why the grasp algorithm isn't really improving the solutions that much. It might have to do with that, and we should look into that. But we did find a couple of instances, well, one instance here, where it did make a difference. If you change the order, then the ramifications are kind of unpredictable, and you might and you will find different solutions sometimes. Mm-hmm. Mm-hmm. Well, he's asking now about waiting times being affected by dwell times and the way they are related to total demand. And even though that's true, there's another congestion effect there. That's not an effect we are dealing with here, partly because that's one of the that was my research when I was doing my master's degree thesis, and my conclusion was that that problem is way too hard to solve, and the effect is not that important compared to the other effects. I think that the increase in waiting times because of overcrowding is an effect that is more important than the other one. And as I didn't mention this, but we're working with assignment, and we're finding solutions where capacity is not constraining. But another line of work, another future research we should do at some point is trying to solve these kind of problems, but using equilibrium models, where you do take into account congestion of different types. But that's a different story, and for what I've seen, this equilibrium models for public transport work with really tiny corridors. So it's not really applicable so far, for what I know.
Okay, Juan Carlos Muñoz says, great talk on everything. Can you comment on your last finding that it will happen when increasing the frequency and service while keeping everything cost identical? We may move from a feasible to an unfeasible solution.
All right, so let me repeat the question because Juan Carlos wants me to talk about one of our recent findings that we have discovered by working with a simplified mathematical model for the problem, which doesn't involve solvers or algorithms, just working with paper and pen and solving equations. We found that there's this situation that you can find where you can be in a situation where the solution is feasible, people are happy taking their express or regular services, and everybody is comfortable in their buses, and then suddenly you increase the frequency of an express service, and instead of improving the situation as common sense would dictate, you might end up making it worse for everyone. And how is this possible? Well, the thing is that there's this threshold of frequency of the express service where it is attractive enough so people are going to stop using the regular service. So if you exceed this frequency, if you start with a frequency that is below this threshold, and then you increase and you exceed this threshold, you might end up in a situation when you're capturing a whole new bunch of passengers, people that are not willing to take the regular service anymore, and now they are going to wait for the express service without really increasing the capacity that much. So this gets you inside this danger zone where you have these frequencies that lead you to infeasibility, and to get out of this zone, you have to reduce express service capacity or increase it. But you can't stay there in this weird part of the domain of frequencies. So this is our latest finding, and we're writing something now, and I think we're going to start presenting these results in conference pretty soon. Mm-hmm. All right. So thanks for being here, and to the people watching the webinar from different places in the world. Thank you for your attention, and see you soon.